On October 30th, 2025, 22 hours after Comet 3IR Atlas reached its closest point to the Sun, Harvard professor Avi Loeb opened the secured terminal in his lab and saw data that forced him to completely reassess the object. The numbers on the screen didn't just differ from expectations, they contradicted everything humanity knew about comets from 3 centuries of systematic observation. The object's brightness exceeded any comet in the solar system at a comparable distance. Not by 10%, not by 50, by an order of magnitude. And this was just the first anomaly on a list that would stretch to 7 pages of technical report by evening. Drop a comment and let us know where you're watching from and how much time you've got. Because we're about to unpack the story of an object that forced scientists to rethink the line between the natural and the artificial. To understand what made that morning significant, we need to go back 4 months to July 1st, 2025. The Atlas telescope in Chile, part of an early warning system for asteroids, picked up a moving point of light in the constellation Hercules. The first day of observations didn't raise any red flags, just another interstellar visitor, the third one in 7 years after Oumuamua and Comet Borisov. The object got the designation 3I Atlas, where the 3 marked it as the third interstellar guest. The I stood for interstellar, and Atlas identified the system that discovered it. Standard procedure, routine work, but the cosmos rarely follows human expectations. By mid-July, it became clear that 3I Atlas had an elongated shape and was surrounded by a green coma, a cloud of gas and dust typical of comets. The green color indicated the presence of diatomic carbon, a molecule that glows with that characteristic hue when hit by solar radiation. Everything looked predictable. An interstellar comet was approaching the inner solar system, heating up, starting to outgas, a process called sublimation. Scientists were gearing up for months of calm observation, collecting spectral data, refining the orbit. Nobody expected that in 3 months, this object would push one of the world's most famous astrophysicists to publicly announce an upgrade in its technological origin rating. Avi Loeb wasn't a random player in this story. Former chair of Harvard's astronomy department, director of the Institute for Theory and Computation at the Harvard-Smithsonian Center for Astrophysics, author of over 900 scientific publications, his name carried weight in the scientific community. But for the last 8 years, Loeb had become known to the general public for his willingness to publicly discuss the possibility of extraterrestrial technology. After Oumuamua passed through the solar system in 2017, he published a series of papers where he didn't rule out the object's artificial origin. Colleagues criticized him for premature conclusions. The public called him either a visionary or a fantasist, but Loeb kept methodically collecting data. In 2023, he developed his own classification system, a scale for rating the technological origin of astronomical objects, a 10-point scale where 0 meant absolutely natural, fully explainable by known physics, and 10 meant confirmed alien technology. The system wasn't officially adopted by the scientific community, but media and space enthusiasts picked it up fast. When 3I Atlas was discovered, Loeb gave it an initial rating of 2 out of 10. An interesting interstellar object with potential anomalies requiring observation. A standard assessment for any interstellar comet. August and September were spent accumulating data. Dozens of observatories worldwide pointed their instruments at 3I Atlas. The James Webb Space Telescope conducted a series of spectral observations. The European Southern Observatory used the Very Large Telescope to capture high-resolution images. Data flowed into international databases where hundreds of astronomers analyzed every pixel, every spectral line, and gradually, oddities started to emerge. First, an absence of iron in the spectrum despite clear presence of nickel. For natural objects, this was unusual, but not impossible. Maybe the comet formed in a region of the protoplanetary disk with anomalous chemistry. The second oddity appeared at the end of September, when 3I Atlas got close enough that details of its structure became visible. Beyond the main tail pointing away from the sun due to solar wind pressure, the comet had an antitail, a secondary tail pointing toward the sun. This phenomenon is known for some solar system comets, when large dust particles lag behind the comet's orbital motion and create the illusion of a forward-pointing tail. But 3I Atlas's antitail was too pronounced, too stable. Its shape didn't change for days, whereas normal antitails are fleeting and shift within hours. The structure's morphology raised questions. By mid-October, Loeb upgraded the rating to 4. It was a public move, accompanied by a press release where he listed the accumulated anomalies and called for increased observation time on major telescopes. A rating of 4 on his scale meant serious anomalies requiring deep investigation, but insufficient evidence for conclusions about technological origin. It was saying the object deserves attention, but it's too early to panic. The scientific method demands patience. Data accumulation. Testing alternative hypotheses. And the real test lay ahead. The perihelion passage. The closest point in the orbit to the Sun, on October 29, 2025, 3I Atlas reached perihelion at 92 million kilometers from the Sun's surface, roughly 62% of Earth's distance from the star. This was the critical moment. Under maximum heating, the comet should show its true face. If it's a typical icy object, sublimation would intensify. Brightness would rise predictably. The spectrum would show characteristic water, carbon dioxide, ammonia molecules. If something else, the data would be different. Astronomers worldwide didn't sleep that night, observing, recording, calibrating instruments. By morning on October 30th, preliminary results started reaching labs, and they weren't what anyone expected. 3I Atlas's brightness at perihelion exceeded any documented comet at a comparable distance from the Sun. The Great Comet of 2007, Hale-Bopp, McNaught, they all paled in comparison. The object's absolute magnitude reached values that required either an enormous reflective surface area or a powerful internal light source. But even more troubling was the color. Instead of the expected white or yellowish reflected sunlight, characteristic of dust and ice, spectral analysis showed a pronounced blue shift. Not a bluish tint, actual blue. This indicated emission. The object wasn't just reflecting light, it was producing it in the blue part of the spectrum. In comet atmosphere physics, there are several known mechanisms for blue emission. Rayleigh scattering on fine particles, fluorescence of certain molecules, ionized gases in magnetic fields. But the intensity and spectral distribution of light from 3I Atlas didn't match any model completely. There were similarities, partial matches, but no full explanation worked. When scientists build comet atmosphere models, they balance dozens of parameters: ice composition, dust particle size, gas outflow velocity, temperature, density. For 3I Atlas, any combination of parameters explaining the blue color contradicted the brightness data, and the combination explaining brightness made blue emission impossible. It was a puzzle. Adding to the mystery was the continued absence of iron. Spectrometers at several independent observatories confirmed it. Iron spectral lines that should have been clearly visible at this brightness and temperature were absent or at the edge of instrument sensitivity. Meanwhile, nickel registered confidently. In natural cosmic bodies, the iron-to-nickel ratio typically matches solar ratios, roughly 20:1. For 3I Atlas, this ratio was flipped, or measurable iron was essentially absent. They were theoretical models for planetesimal formation in anomalous chemistry regions, but they were exotic, requiring specific conditions in the parent star's protoplanetary disk. The antitail's morphology after perihelion didn't just persist, it intensified. High-resolution images showed a structure resembling not a dispersed dust cloud, but an almost collimated beam of material pointing toward the sun. Some observers noted periodic intensity changes in this structure, with a period around 17 hours, possibly matching the object's rotation, or maybe not. The data hovered at the edge of statistical significance. More time was needed, more observations. But Loeb decided not to wait. On the morning of October 30th, after analyzing the overnight data, Avi Loeb gave an interview to USA Herald, where he officially announced upgrading 3I Atlas's rating from 4 to slightly above 4 on his scale. The phrasing was cautious, but significant. Slightly above 4 meant the accumulated anomalies warrant serious consideration of unconventional explanations, but there isn't yet enough evidence for definitive claims. In the interview, he listed 4 main factors for the decision: extreme brightness, blue emission, anomalous chemical composition, and unusual morphology. And he added a phrase that media seized on instantly: fresh data could push the rating even higher. This phrase wasn't a threat or sensationalism, it was scientific caution. Loeb understood that speaking publicly about possible technological origin meant balancing scientific boldness against reputational risk. Every word would be analyzed by colleagues, every number verified. Upgrading by a fractional amount was a way of saying, yes, the situation has changed, the data demands attention, but we're not jumping to conclusions. The scientific method isn't a race to sensation. It's a slow, methodical approach to truth through verification and re-verification. To understand what slightly above 4 means, you need to understand Loeb's full scale. 0 is a rock, asteroid, comet, meteorite, completely explicable through celestial mechanics and known physics. 1 point means an object with minor anomalies still fitting natural models with some assumptions. 2 points, an interesting object deserving further study. 3 points, an object with unusual characteristics that could have both natural and artificial explanations, with roughly equal probability based on available data. 4 points, serious anomalies poorly explained by natural models, but still possibly explicable through exotic formation conditions or composition. 5 points on this scale would mark the shift toward more radical hypotheses. At that level, natural explanations become strained, requiring multiple unlikely coincidences. 6 points, an object with characteristics far easier explained by artificial origin than natural. 7, an object with clear signs of order or function not typical of natural processes. 8, an object with detectable signals or patterns clearly pointing to intelligent source. 9, an object with confirmed functionality or communication. 10, absolute proof of artificial origin, verified by the international scientific community. 3I Atlas at slightly above 4 existed in a zone of scientific uncertainty. Strange enough to demand close attention, but not anomalous enough for revolutionary claims. It was the sweet spot between caution and honesty. Loeb wasn't screaming about aliens. He wasn't writing sensational headlines. He was simply telling the scientific community and the public, this object is unusual. We need to direct resources toward it. We need to observe it carefully while it's still in our reach. Because if we miss critical data now, the next opportunity might never come. If the object's stellar magnitude was the first, most obvious red flag, then the blue color was its kryptonite for conventional astronomy. Blue light. Those are waves around 450 nanometers, high-energy photons born in extreme conditions. When an object glows blue, it's telling you something about temperature, about interaction with solar radiation, about fields of interacting particles and energies. For a comet that should have been glowing with reflected sunlight, pale yellow, characteristic of the sun's color spectrum, blue emission was a massive red flag, or more accurately, a blue one. The night of October 29th, the James Webb spectrographs captured the spectrum of 3I Atlas at the peak of the comet's activity. The processed data showed an unusual intensity distribution in the blue part of the spectrum. When astronomers were used to seeing a smooth continuum of reflected light with absorption lines from gases and dust overlaid on top, 3I Atlas handed them a spectrum where the blue region looked enhanced, with certain structure that resembled, but didn't exactly match, the known spectral characteristics of luminescent material. It was like someone had shined a blue lamp from inside the comet. The possible explanations for blue emission traditionally came down to a few mechanisms. First, Rayleigh scattering on very fine dust particles, which in the upper layers of the comet's atmosphere scatter short wavelength light more than long wavelength. Same reason Earth's sky looks blue when atmospheric molecules scatter sunlight. Second mechanism, fluorescence of molecules that absorb ultraviolet photons from the sun and re-emit them in the visible spectrum, including the blue region. A known molecule producing blue fluorescence in comets is carbon derivatives. Third mechanism, ionized gases in a magnetic field which can produce blue emission through excitation and recombination processes. All three mechanisms were real and happened in various solar system comets. But all three mechanisms had one thing in common. They should produce specific spectral signatures predictable by physics. When the spectrometrists on James Webb started breaking down 3I Atlas's spectrum looking for these signatures, they found partial matches but no perfect fit to any model. Rayleigh scattering should have given a smooth, monotonically rising continuum towards shorter wavelengths. But 3I Atlas had structure, small peaks that didn't match simple scattering. Fluorescence of known molecules should have shown certain discrete lines, but the spectrum was blurrier, more continuous. Ionized gas should have shown bright lines of atomic emission, and they were there, but faint, not enough to explain the overall intensity of the blue light. This wasn't a mystery in the sense that explanation was impossible. It was a mystery in the sense that it required a combination of conditions that seemed unlikely. You'd need to assume multiple mechanisms acting simultaneously, each contributing to the blue color, but none dominating completely. Or you'd need to assume that chemical processes were happening in the comet's upper atmosphere that astronomers had never observed before. It was like trying to assemble a puzzle where several pieces fit perfectly, but the big centerpiece keeps slipping from your hands. The scientific community had developed a system for responding to these situations. When observations don't match expectations, three main paths emerge. First path, acknowledge an error in the data, calibration error, or analysis mistake. This happens often in astronomy because instruments are complex and sources of error are numerous. Second path, propose an expansion of known physics, search for exotic but still natural explanations. Third path, start carefully considering alternative hypotheses. By October 30th, astronomers were still working through the first path. Data was recalibrated. Different instruments cross-checked each other. And when calibration confirmed the original results, attention shifted to the second path. The second pillar of 3I Atlas's anomalies was chemical composition. Spectral analysis identified the presence of many elements: carbon, oxygen, hydrogen, nitrogen, exactly what you'd expect from a typical comet. But when spectrometrists started looking for a trace of iron, they hit nothing. Iron. It's the king of Earth's crust and planetary interiors. Iron makes up about 5% of Earth's crust and roughly 35% of Earth's core. In the solar system, the iron-to-nickel ratio in meteorites and asteroids roughly matches the Sun's, about 20-to-1 by mass. Comets have less iron because they formed in the cold regions of the protoplanetary disk, where volatile elements dominated. But iron was still there. Even in the lightest, iciest comets, iron registered confidently. For 3I Atlas, iron was either absent or at the edge of the instrument's sensitivity. The iron spectral line at 3050 angstroms, the classic indicator of this element's presence, didn't appear in the spectra recorded by James Webb. Attempts to find it at other wavelengths, other spectral lines, nothing. Meanwhile, nickel looked clearer. This was deeply strange. It was like finding a human without calcium in their bones that somehow stayed strong and functional. Nature usually doesn't create such anomalies. It works through patterns, and when patterns break, it often points to a cause more complex than simple variation. There were theories that could explain such an iron deficit. One theory said the object formed in a specific region of the protoplanetary disk, where chemical separation of elements occurred under temperature gradient or magnetic field influence. Another theory considered the possibility of secondary processing of comet material by radiation or particles during its journey through interstellar space, which could preserve light elements while stripping iron from the upper layers. A third theory, which scientists preferred not discussing publicly, suggested construction, not in the sense of factory assembly, but modification. If the object had been created with a purpose, say to minimize magnetic interactions, it would be designed with minimal magnetically active elements. Iron is one of the most magnetic elements. The third pillar of the anomalies was morphological, and it was the most visually striking. When high-resolution photographs of 3I Atlas appeared in scientific databases, astronomers started noticing details that didn't fit the typical comet image. Comets usually have a diffuse appearance: cloud of gas and dust, gas tail that melts and expands as it moves away from the sun, often asymmetrical, often irregularly shaped, the natural disorder of a natural object. But 3I Atlas's antitail, the part of the comet's tail created by lagging large dust particles not fully subject to solar wind pressure, looked almost collimated, almost like a beam, almost like someone had taken a flashlight and pointed it at the sun. Collimation means parallel structure, order, directedness. This is a property more characteristic of technological objects than natural ones. When scientists aimed high-resolution optical instruments at the antitail, they distinguished structure, fine lines, almost like rays, periodic intensity fluctuations, and most intriguing, temporal stability. Normal comet antitails change shape within hours because the interaction of solar wind with dust particles is a dynamic, turbulent process. 3I Atlas's antitail remained relatively stable over days of observation. The shape changed, but slowly, systematically, almost as if controlled by some force. When astronomers started analyzing the periodicity in the antitail's intensity changes, they found a signal with a period around 17 hours. This matched the predicted rotation period of the main comet nucleus, calculated from brightness variations in other observations. The match was too good to be simple coincidence, but it also wasn't impossible from the perspective of natural physics. If the comet's nucleus rotates quickly, active outgassing regions on its surface would also rotate, leading to periodic changes in the comet tail's structure. This was an explanation that worked, but required assuming the comet's rotation was extraordinarily fast. Its outgassing aimed in a direction not quite natural, and its dust had unusual size and distribution. The fourth pillar of the anomaly brought us back to brightness, but in more complex context. The object's stellar magnitude measured at perihelion required the comet to have either a massive reflective surface, over 300 meters in diameter based on assumed ice albedo, or a powerful internal light source or scattering ability. But high-resolution images showed the comet's main nucleus. The visible solid part was small. Preliminary estimates said between 100 to 150 meters. The gap between the expected object size needed to explain the brightness and the actual observed size was critical. The object was glowing brighter than it should have been. You could introduce additional variables into the model. Maybe the comet nucleus had extraordinarily high albedo, reflecting 90% of incoming light instead of the expected 25%. Maybe the comet had a huge, expanded gas halo we weren't seeing clearly, and that halo scattered light. Maybe exotic chemical reactions were happening in the coma's upper layers, releasing energy. All these explanations were physically possible in principle, but all required a combination of conditions astronomers had never observed simultaneously in one object before. And when you start multiplying the probabilities of unlikely events, the limit of what you can explain as a series of coincidences starts approaching. Avi Loeb, in his USA Herald interview the morning of October 30th, structured his explanation around exactly these four pillars: extreme brightness, blue emission, absence of iron with nickel present, the antitail's morphology with periodic structure. Each pillar was backed by data. No single pillar proved technological origin on its own, but the four pillars together, the entire architecture of anomalies, posed questions traditional astronomy wasn't rushing to ask. In his interview, Loeb didn't claim 3I Atlas was an alien probe or a spacecraft or some civilization's artifact. He simply said the data demanded attention, that the technological origin hypothesis should be considered as one possibility, and that disproving this hypothesis required additional observations. This was important to understand. The rating upgrade wasn't a cry of paranoia or sensationalism. This was scientific analysis of data. When you see an anomaly, you study it. That's the foundation of the scientific method. Hypotheses are tested against facts, and if facts don't match the current paradigm, you either expand the paradigm or consider alternative explanations. Loeb was doing exactly that. He wasn't claiming truth, he was suggesting a direction to look. And the international astronomy community listened. Within hours of Loeb's interview, observatories worldwide reassigned their telescopes. The queue for observing 3I Atlas on James Webb grew longer. The European Southern Observatory allocated additional observation time. Even China's astronomy service announced a special comet monitoring program. An orange alert level replaced the quiet of the autumn sky. When Professor Avi Loeb gave his interview to USA Herald on the morning of October 30th, 2025, he couldn't fully anticipate the scale of response his words would trigger over the next few hours. An upgrade by a fractional amount, from 4 to 4 and change, sounded modest to a public accustomed to sensations and clear-cut answers, but to the scientific community, it was an earthquake. The technological origin scale, which seemed like a theoretical construct, a tool for making sense of data, suddenly got practical application. It stopped being an academic game. It became a way to talk about the impossible in a language any scientist could understand. The first hours after the interview passed in digital chaos. Emails flew between observatories, between national astronomy councils, between scientific journal offices. The director of the European Southern Observatory in Chile, where one of the world's most powerful ground-based telescopes sat, the Very Large Telescope with its 76-meter primary mirror diameter, received an official request for additional observation time on 3I Atlas. This wasn't an ordinary request. Normally, such requests took weeks, sometimes months to process and coordinate among competing research groups. But this one went through in 3 hours. The director personally approved the reallocation of observation time. The priority of a comet that weeks earlier seemed like just another interstellar traveler was raised to maximum. Japan's National Observatory on the Hawaiian Islands made a similar move, reassigning the 8-meter Subaru telescope for extended observations of 3I Atlas. The Chinese Science Council announced a special program where the constellation Hercules, home to the comet, would be monitored by China's largest telescopes for the next 2 weeks. Even Russia, despite complex geopolitical conditions, managed to coordinate observations using specialized instruments housed at the Special Astrophysical Observatory in the Caucasus. 3I Atlas was becoming the center of world astronomy's attention, not because it was the brightest comet, not because it was the closest, but because it was the strangest. To understand the scientific community's reaction, it's important to grasp the structure of academic hierarchy and the weight Avi Loeb's voice carried in that system. Loeb was the author of over 900 scientific publications, most cited thousands of times. His name appeared in astrophysics textbooks. His work on gravitational lensing and dark matter had fundamental importance for modern cosmology. When such a person says data demands attention, other scientists listen. But that didn't mean everyone agreed with his assessment. Online, in closed astronomy forums, at virtual and in-person conferences, a lively discussion began. Skeptics pointed out that the rating upgrade was based on incomplete data. Yes, 3I Atlas was unusual, but unusual didn't equal impossible. As one prominent planetologist from Princeton University argued, astronomy's history is full of objects that seemed anomalous at first observation, but found natural explanations under deeper analysis. His argument was logical and fair, but those supporting a more radical interpretation of the data, those who'd followed Loeb's work over the last 8 years, pointed out that the rating upgrade wasn't a hasty decision, but the result of months of accumulating and analyzing facts. Loeb wasn't saying he had proof. He was saying the anomalies were serious enough to reclassify the object into a higher attention category. To fully grasp this discussion, you need to understand how Loeb's scale works in practice, under what conditions an object moves from one level to another. Level 0 on the scale is a rock. An asteroid like Vesta, orbiting the sun for billions of years, following celestial mechanics laws, completely explicable by gravity, solar radiation, and known physics. When astronomers observe such an object, they expect certain things: a spectrum matching silicate or metallic rock, an orbit following Kepler's laws, absence of unexpected accelerations or decelerations. 0 means complete alignment with expectations. Level 1 is the first step up the scale. At this level, an object has minor anomalies, still explicable by natural causes with some assumptions. For example, an asteroid with a slightly unusual spectrum that could indicate either exotic composition or secondary radiation processing, or a comet with unexpectedly high activity, explicable by elevated volatile content. At level 1, an object deserves additional study, but no need to panic. It's an object worthy of scientific curiosity, but not revolutionary. Level 2, an object deserving serious investigation. At this level, anomalies are more pronounced, more systematic, but still fit within natural physics with expanded models. This could be a comet with unusual morphology explicable by specific nucleus orientation and distribution of active regions on its surface. This could be an asteroid with unusual spectral characteristics explicable by cosmic ray impacts on its surface over millions of years. At level 2, an object enters a class requiring specialized attention, but conventional astronomers don't consider it cause for urgent concern. Level 3 is the point of no return in object classification. At this level, anomalies become serious, and natural explanations start requiring more and more additional assumptions. At level 3, natural and artificial hypotheses are roughly equal in probability based on available data. This doesn't mean scientists think the object is alien technology. It means they must consider this as one possibility alongside other exotic but still natural explanations. At this level, the object transitions into a category requiring serious consideration of alternative models. Level 4 is the territory of serious anomalies. At this level, an object has characteristics poorly explained by natural models, but still possible under exotic formation conditions, composition, or secondary processing. At level 4, natural explanations require many unlikely coincidences. An object at level 4 demands close attention from the international community, allocation of additional observation resources, coordinated data analysis. But an object at level 4 isn't proof of extraterrestrial origin. It's assigned to look more carefully. It's an object requiring metamorphosis of our understanding, either toward atypical natural physics or toward questions society has been reluctant to ask itself. Level 5 marks the shift to more radical hypotheses. At level 5, natural explanations become strained, requiring so many unlikely coincidences they lose status as reasonable alternatives. At level 5, scientists begin seriously considering the technological origin hypothesis not as absurdity, but as one possibility that can't be ruled out. At this level, the probability that the object is a product of intelligence becomes significant, though natural alternatives still exist, harder to refute. At level 5, international organizations like the United Nations might begin urgent discussions about responding to the possibility of extraterrestrial contact. Level 6, an object with clear characteristics far easier explained by artificial origin than natural. At level 6, the object's functionality, its structure, its behavior indicate intelligent design with probability exceeding 50%. At this level, even conservative scientists must wonder how the object could have been created, what its purposes are, where it came from. At level 6, science begins transitioning from mental exercise to practical readiness for encountering the unknown. Levels 7, 8, 9 are increasingly explicit evidence of artificial origin. At level 7, an object demonstrates clear order or functionality, not characteristic of natural processes. At level 8, an object shows registered signals, patterns, or communication clearly pointing to intelligent source. At level 9, an object demonstrates confirmed functionality or active contact. And level 10, absolute, irrefutable, internationally verified proof of artificial origin and intelligent source. 3I Atlas. At level 4 plus a small increase sat in that classification zone where science and the unknown began touching each other. Not at the far end of the spectrum, nowhere near the "we met aliens" section, but not at the beginning either, where you could easily classify the object as routine interstellar phenomena. This was a boundary, a thin line, where caution met curiosity, where methodology touched excitement. At this level, scientists had to be ready for two things: that the data would guide them toward expanded understanding of natural physics, or that they'd be forced to ask questions that weeks earlier seemed impossible in the context of academic science. The international community's reaction varied depending on national context and cultural specifics. In the United States, Loeb's message was received as a signal to reassess funding priorities. The National Science Foundation allocated an additional $1 million to 3I Atlas research within hours of the interview. the European Space Agency convened an urgent meeting of its scientific committee to discuss possibilities for using its instruments for prolonged comet monitoring. In Europe, where tradition for restraint in scientific claims was even stronger than in America, they still recognized that Loeb's data demanded attention. This wasn't agreement with his conclusions. It was recognition of the object's importance. In Russia, the scientific community faced a dilemma. On one hand, Russian space research tradition, the legacy of the Soviet school, demanded serious treatment of any unusual cosmic phenomena. On the other hand, Loeb's remark about technological origin, that the object might be something artificial, raised political questions. If it was alien technology, where did it come from? Was this a potential threat? The director of the Special Astrophysical Observatory released an official statement saying Russia was ready to coordinate observations with the international community and that all scientific data would be open to the world's scientific community. This was a cautious but clear position. Yes, we're looking. Yes, we're listening. And yes, we're ready to be part of solving this mystery together with the rest of the world. In China, the reaction was faster and more ambitious. The Chinese Academy of Sciences announced a special observation program engaging the country's largest telescopes over the next 2 weeks. The program was called Project Integrity, a symbolic name suggesting integrity in the face of the unknown, integrity in acknowledging that the object's traditional classification might be incomplete. This wasn't panic. It was mobilization. The scientific community, despite national borders and geopolitical disagreements, suddenly found common ground in the language of data. Within the first 12 hours after Loeb's interview, over 400 astronomers from 28 countries announced their readiness to include 3I Atlas observations in their research programs. This wasn't a conference, not a formal assembly, but a spontaneous wave of coordination arising from understanding that science faced an object demanding attention, demanding joint effort, demanding that national borders temporarily give way before the facade of the unknown. Loeb's scale, which hours earlier seemed like a theoretical construct, suddenly became a practical tool for organizing humanity's scientific activity. And this was the beginning of something new. On October 30th, 2025, the very day Avi Loeb upgraded 3I Atlas's rating, observatories around the world entered their first night of intense observation. This wasn't a night of routine work. It was a night when hundreds of astronomers, usually scattered across different projects, looked in one direction, observed a single object, accumulated data at unprecedented intensity for this comet. The Western Hemisphere, home to the United States, Chile, and Mexico, was just entering evening. The Eastern Hemisphere, including Europe, Asia, and Australia, was preparing for day. Thanks to this planetary geography, 3I Atlas hung above the horizon in either the Western or Eastern Hemisphere almost continuously. The comet couldn't hide from scientific scrutiny. It couldn't escape the scientific gaze. At the Very Large Telescope in Chile, the same country where the 8-centimeter Atlas telescope discovered the comet 4 months earlier, the spectrograph was reoriented from other research projects and aimed at 3I Atlas. The Very Large Telescope, consisting of 4 main 8-meter telescopes and 6 auxiliary 1.5-meter telescopes, could resolve details the other instruments could only guess at. Spectral data transmitted to the monitor in real time showed the structure of light scattered and emitted by the comet, with resolution sharp enough to distinguish individual anomalies in its atmosphere's composition and structure. And the first hours of observation confirmed what James Webb's nighttime observations had suggested 24 hours earlier. The blue color was real. It wasn't a calibration artifact, not a data processing error, not an illusion created by observation conditions. When two independent instruments 14,000 kilometers apart gave identical results, this stopped being a matter of belief. It became fact. The Very Large Telescope's spectrograph split the light from 3I Atlas into its component wavelengths like a prism splits white light into a rainbow. And in the blue part of the spectrum, in the wavelength region from 420 to 450 nanometers, there were excess photons, more light than simple reflection of solar radiation should produce. Emission, radiation. The object was glowing blue because something inside it was producing blue light. When astronomers started searching for the source of this light, they hit a paradox. Blue light is usually produced by hot, excited electrons that recombine and emit photons of specific energies. The comet atmosphere's temperature at 92 million kilometers from the sun shouldn't exceed a few hundred Kelvin. At that temperature, processes producing blue light should be unlikely or practically impossible. But the data showed the light was real. This meant either processes were happening that astronomers didn't expect, or the light source wasn't just from material being heated by solar radiation. This meant 3I Atlas either had an internal energy source or a mechanism for converting external energy into blue light, something different from anything scientists had observed before. At Japan's Subaru Observatory on the Hawaiian Islands, observations used adaptive optics, technology that corrected Earth's atmospheric distortions in real time, allowing images almost as sharp as if the telescope were in space. The images obtained showed 3I Atlas's morphological details with unprecedented clarity. The comet's main nucleus, the solid body around which the gas-dust atmosphere formed, looked elongated, almost cylindrical. The object's length was roughly 120 meters, diameter about 40 meters. If this were an icy object, such proportions wouldn't be unusual for an interstellar comet. But details of its surface showed something strange. At one end of the nucleus were structures that seemed too regular, too geometric for natural formation. These weren't mountains and valleys like you usually see on asteroids, results of billions of years of meteorite bombardment and weathering. These were lines, almost like ridges, almost like the nucleus wasn't a random-shaped ice chunk, but an object with intentionally created geometry. The image was sent to the database in real time, and within hours, a spectrum of interpretations began expanding online. Some scientists said this was pareidolia, the psychological phenomenon where people see familiar patterns in random data, like seeing faces in clouds. Others insisted it was real geometric structure, a product of either natural erosion, creating regular patterns, or something more intriguing. The debates were intense, but the data remained still. 3I Atlas had visible surface structure. At the European Southern Observatory in Chile, spectrometrists continued analyzing the comet's chemical composition. The absence of iron remained a mystery, but now they had data high quality enough for more detailed analysis. They could determine not just the absence of iron in the gas phase, the gases the comet emitted, but also its absence in solid dust particles. Iron wasn't frozen in the comet nucleus's ice, wasn't in the form of iron-bearing minerals in the dust the comet ejected into space. It was complete, systematic absence. Meanwhile, nickel was detected in both gas phase and solid particles. The nickel-to-iron ratio was opposite to the solar ratio by several orders of magnitude. A young astrochemist from Munich University, working the night shift at the European Southern Observatory, proposed a hypothesis both logical and troubling. If the object had been constructed to minimize magnetic interactions, its designers would have chosen non-ferromagnetic materials. Iron is one of the most magnetic elements. Nickel is also magnetic, but to a lesser degree. Under certain processing and temperatures, nickel can be made non-magnetic or weakly magnetic. The young astrochemist wasn't claiming this proved artificial origin. He simply proposed an interpretation of the data. But this interpretation pointed to a possibility standard astronomy preferred not to consider. In China, at an observatory on the Tajihei Plateau, a telescope aimed at 3I Atlas to obtain polarimetric data, information about how light reflected or emitted by the comet becomes polarized. Light polarization tells about the structure and composition of scattering material. For natural, icy, and dusty comets, polarization has a predictable form depending on dust particle size and composition. Data from Tajihei showed a polarimetric signature that didn't match predicted models. It was like trying to assemble a puzzle only to realize you've been looking at the wrong picture the whole time. Each new instrument, each independent observation from another observatory, added not clarifying facts, but new questions. By the end of October 30th, 24 hours after Loeb's interview, over 5,000 individual observations of 3I Atlas had accumulated in scientific databases. That was an enormous amount of data gathered by astronomers worldwide using telescopes ranging from small, about 1 meter diameter, to the largest 8-meter instruments. Each observation contained information: spectral data, polarimetric data, direct images, time series showing the object's brightness variations over time. A wave of coordinated scientific activity swept through the astronomical community. This wasn't panic. It was focus. A methodical, systematic attempt to understand what lay before them. And the results of this first night of intense observation began pointing toward a direction that seemed impossible in official science a week earlier. The data didn't say 3I Atlas was alien technology. The data simply said the object was more complex, more interesting, more anomalous than initial theories assumed. The data said you needed to look further, dig deeper, expand search horizons. And as the evening of October 30th transitioned into night, as Earth continued rotating around the sun and 3I Atlas continued moving through the solar system, a new reality emerged. A reality where what we thought about comets, about interstellar objects, about the boundaries between natural and artificial, had to be reconsidered. This was a reality humanity began truly grasping for the first time that night. In the early hours of November 1st, 2025, when half the Earth was in half sleep and the other half prepared for day, a group of mathematicians and statisticians gathered in the office of the Harvard-Smithsonian Center for Astrophysics in Cambridge, Massachusetts. They weren't astronomers in the traditional sense, the kind who look through telescopes and marvel at cosmic beauty. They were calculators, people who fed data into computers and asked machines to tell them the story hidden in the numbers. Avi Loeb invited them to an informal meeting because he realized the overnight observations had accumulated enough information for statistical analysis. They needed to understand how likely it was that 3I Atlas could display this particular combination of anomalies. And here, mathematics of improbability entered the stage. One of the invited specialists, a statistician named Mark Hamilton from MIT, started with a simple question. If we randomly selected an interstellar comet from the imaginary population of all possible interstellar comets, what would be the probability it simultaneously had all 4 anomalies 3I Atlas displayed? The probability of being brighter than a standard comet at that distance by an order of magnitude was roughly 1 in 1,000. The probability of demonstrating blue emission unexplainable by known mechanisms was roughly 1 in 500. The probability of iron absence with nickel present was roughly 1 in 150. The probability of structured antitail morphology with periodic structure was roughly 1 in 200. When Hamilton multiplied these probabilities together, assuming they were independent, the result was staggering. the overall probability that a random comet would show all 4 anomalies simultaneously came to roughly 1 in 50 million. This was a number that needed to be spoken slowly to grasp its meaning. 1 in 50 million. About 8 billion people live on Earth. If each person randomly selected one interstellar comet, the probability that at least one would show all 4 anomalies was roughly 1 in 6,000. Incredibly unlikely, but not completely impossible. But when Hamilton added the additional observations made during the night, when the number of known anomalies grew from 4 to 7, the probability dropped even lower. Now you had to add the probability that light polarization would deviate from expected values according to known models. The probability that the absolute spectral signature wouldn't match any known comet in a database of 380 comet spectra collected over half a century of observation. The probability that the antitail would show periodicity matching rotation, but with such extraordinary precision, it seemed too good to be random. When Hamilton multiplied the probabilities again, his colleagues leaned closer to the computer screen to see the result. 1 in 2 billion. This was a probability at which alternative explanations needed serious consideration, because when the probability of an event drops below a certain threshold, science typically uses a threshold of 1 in a million or 1 in 100 million, serious revision of assumptions begins. Either the probabilities you used in the calculation were wrong, or your model of the world was incomplete, or something was happening you hadn't accounted for in your initial calculations. It was a reminder that the mathematics of statistics had its own voice, and that voice was saying something important. However, Hamilton was honest and experienced enough to understand the trap in this analysis. He raised his hand, offering clarification. The probabilities he'd used were based on the assumption that anomalies were independent. But what if they weren't? What if one anomaly caused another? For example, if the object had unusual chemical composition, it could explain both the iron absence and unusual tail morphology. If they properly accounted for correlations between anomalies, the probability might be higher. This was an important caveat, an honest acknowledgement that statistics, like any analytical tool, had limits. But limits didn't mean incorrectness. It simply meant caution was needed in interpreting results. Another statistician in the room, Jasmine Parker from Yale University, proposed an alternative approach. Instead of calculating the probability that a comet would show all these anomalies, let's calculate the probability that all these anomalies would arise independently by pure chance, given what we already know about the object. This method, called Bayesian updating, allows you to reassess probabilities as new information arrives. Starting from a neutral position, that 3I Atlas was equally likely to be a natural comet or something with artificial characteristics, Parker began updating this probability each time new evidence appeared. After the first anomaly, extreme brightness, the probability of a natural explanation shifted slightly toward natural origin, but stayed close to 50%. After the second anomaly, blue emission, the probability of natural explanation dropped to 45%, because blue emission was rarer and harder to explain. After the third anomaly, iron absence, the probability dropped to 35%. After the fourth, structured antitail morphology, the probability dropped to 25%. After the fifth, sixth, and seventh anomalies discovered during overnight observations, the probability of purely natural origin dropped below 10%. This didn't mean 3I Atlas was artificial with 90% probability. Bayesian analysis showed something more subtle. It showed that as evidence accumulated, the probability that all these anomalies arose from simple chance or from known natural processes steadily declined. That meant either our understanding of natural processes needed expanding to allow for mechanisms astronomers hadn't previously observed, or we needed to seriously consider alternative explanations. And the only alternative scientists reluctantly but seriously were considering was one involving technology or construction. Avi Loeb listened to this analysis with an expression mixing intellectual satisfaction and scientific worry. He understood the numbers confirmed his intuition, that data seeming strange on day one became increasingly anomalous as information accumulated. But he also understood that statistics could lead to wrong conclusions if manipulated incorrectly. So when the group prepared the first preliminary report, Loeb demanded it be published with full disclosure of all assumptions, all potential sources of error, all alternative interpretations. The report was titled Statistical Analysis of Anomalies in Spectral and Morphological Characteristics of Interstellar Object 3I Atlas, a modest title for a document containing explosive mathematical conclusions. The report clearly stated that the probability all observed anomalies arose from chance was extraordinarily low, roughly in the range of 1% or less. But the report also stated this didn't mean 3I Atlas was artificial. It only meant other explanations were needed. Either there were natural processes astronomers didn't fully understand, or the object had been created or modified by something or someone. The report was a sculpture of caution, built from solid mathematical stone. When the report was posted to the Archive server, the preprint archive where scientists publish before official review, it received over 10,000 downloads within the first 3 hours. This was unusual for statistical analysis of astronomical data. Typically, such papers got downloaded hundreds of times, maybe thousands over a week. But 10,000 in 3 hours indicated something different, indicated the world was hungry for information, for attempts to understand what was happening with 3I Atlas. Comments started arriving from every corner of the astronomy community. Some criticized the methodology, claiming assumptions were too optimistic toward unusualness. Others argued the analysis wasn't bold enough, didn't fully explore the most radical data interpretations, but all agreed on one thing: the analysis deserved attention. The mathematics of improbability had its own language, and that language spoke clearly. The chances that 3I Atlas was just an ordinary comet with an unusually large number of coincidences were extremely slim. It was a scientific acknowledgement that the object lay beyond the boundaries of normality, and if an object lay beyond the boundaries of normality, then either normality needed expanding, or you needed to find new boundaries, new categories, new ways of understanding what could exist in space. On November 1st, 2025, exactly 24 hours after Avi Loeb's interview, the silence of the scientific establishment, which had long avoided public discussion of extraterrestrial technology, finally broke. And it didn't break quietly. It broke into a loud, multi-voiced conversation that swept through universities, research centers, observatories from Berkeley to Bologna, from Beijing to Sydney. Each voice had its own tone, some cautious, others critical, still others full of foreboding. But all voices spoke of one thing: that 3I Atlas had stopped being an astronomical curiosity. It had become a phenomenon requiring not just scientific analysis, but philosophical reconsideration of what the universe was capable of. The first to break the chorus of restraint was Professor André Merchant from the University of Geneva, one of the world's leading experts on comet spectroscopy. In an interview with the Swiss newspaper Neue Zürcher Zeitung, Merchant said what many thought but feared speaking aloud. He said the blue emission of 3I Atlas was so unusual that it required either a complete rethinking of how comets form, or an acknowledgement that we were dealing with an object that wasn't a comet in the traditional sense. Merchant was a conservative scientist, someone who'd avoided bold statements and controversial hypotheses over 40 years of scientific career. So when he made such a statement, it carried weight. It meant the data was compelling enough to push a conservative toward discussing the impossible. The response to Merchant's words came quickly from another corner of the world. Professor Katsuhiro Tanaka from Tokyo University, an expert in asteroid and comet morphology, published a preprint proposing an alternative explanation. Maybe, Tanaka said, 3I Atlas wasn't a comet or technology, but a transitional class object never previously observed, an object resulting from a collision of two small bodies or fragmentation of a larger object under conditions that gave it unusual characteristics. This explanation was logical, physically possible, but equally required acknowledging that the universe contained categories of objects scientists hadn't yet cataloged or fully understood. In the United States, pressure on official institutions began mounting. Journalists started asking NASA representatives whether there was an official action plan if 3I Atlas turned out to be technology. The official answer was diplomatic. NASA stated the agency was carefully monitoring the situation, coordinating observations with the international community, and that any conclusions about the object's nature would be based on solid scientific evidence. But in the corridors, in the halls of administration, quiet panic began. If 3I Atlas was extraterrestrial technology, it meant we lived in a universe where such technology exists and can arrive in our solar system. It meant decades of searching for extraterrestrial intelligence might end not as expected, not with a radio signal, not with an attempted contact, but with a physical object appearing, whose intentions and capabilities were unknown. The United Kingdom, through its Royal Astronomical Society representative, issued a statement supporting Loeb's approach to data evaluation. The society acknowledged that historically, the scientific community had been overly conservative in approaching questions about extraterrestrial technology, and that the time had come to reconsider this conservatism. This was symbolic because the Royal Astronomical Society is one of the world's most prestigious and respected scientific organizations, founded in 1802. When an organization of that level expressed support for radical reassessment of an object, it meant a paradigmatic crack had appeared in scientific thinking. France and Germany coordinated their approach through the European Organization for Nuclear Research, CERN, and announced a joint program analyzing 3I Atlas data. This wasn't simply a scientific initiative. It was a political demonstration that Europe was serious about its approach to the object. European scientists proposed using the most advanced computational resources available on the continent to conduct analysis at a level impossible using only individual national observatory resources. The plan included collaboration with Eastern European scientists, including Russian and Ukrainian specialists. Despite current political disagreements, this was acknowledgement that facing the unknown, national borders and historical conflicts stepped into the background. Russia, through its chief astronomer, issued a more cautious but no less significant statement. The chief astronomer said Russia didn't exclude the possibility that 3I Atlas might be something unusual, and that Russian scientific tradition, with its long history of space exploration, was ready to participate in this research on a completely open basis. This was an important diplomatic gesture, because it meant that even amid international tension, the scientific community was ready to set aside political disagreements for an unraveled cosmic mystery. India announced its space research organization would provide data from Indian spacecraft for 3I Atlas analysis. This meant even countries traditionally sidelined from mainstream space research began seeing 3I Atlas as an opportunity to contribute to one of the century's most important investigations. Small African countries without their own space programs began expressing interest in being included in the data analysis process, providing computational resources, people, equipment, everything they could offer. The media landscape that night and day underwent transformation. The internet flooded with articles, videos, podcasts about 3i Atlas. But surprisingly, most of this content wasn't sensational, wasn't panicked. People spoke calmly about the data, tried understanding what the blue color meant, the iron absence, the structured morphology. There were certainly those seeing 3i Atlas as a sign of the end times or the arrival of aliens. But most of the internet was occupied with meaningful discussion, attempts to understand what was happening. This was a moment when collective human consciousness reached a certain level of readiness for the idea that the universe might contain something beyond what we knew. Avi Loeb, at the center of this attention, remained surprisingly calm. He gave a series of interviews, but in none did he exceed the boundaries of data. He didn't claim 3i Atlas was an alien ship. He didn't say proof of extraterrestrial life had been found. He simply pointed to the data, to the anomalies, to the questions needing to be asked. His constant emphasis on uncertainty, his refusal to draw final conclusions, his humble acknowledgement that he didn't have the answers, earned great respect even from critics. Because this was science in its purest form, honest, methodical, open to new ideas but not hasty in conclusions. By the end of November 1st, 2025, 3i Atlas had stopped being a matter of purely astronomical interest. It became a symbol of something larger, the possibility that the world we live in could be more interesting, more complex, more filled with wonder than seemed days earlier. And most importantly, it became a unifying force. In a divided world where it often seemed more divisions separated people, nations, ideas, than unity bound them. 3. Atlas reminded people that certain things exist larger than all our disagreements. Certain things require unity, cooperation, our collective intelligence directed toward one goal: to understand the truth. On November 2nd, 2025, as the world woke to dawn in different time zones, something happened in the scientific community that seemed impossible 2 days earlier. It wasn't a revolution in the sense of open rebellion, but rather water slowly finding a new channel. The consensus that had held firm, the consensus that extraterrestrial technology was a topic for science fiction, not serious astronomy, began eroding. And it eroded not because of sensational claims, but because of boring, methodical data, because of numbers, because of spectra, because when you direct enough eyes at one object, the object starts telling you its secrets, even if you don't like those secrets. The first morning of November 2nd brought a wave of new observations. Through the night, several independent observatories working in parallel conducted detailed monitoring of 3i Atlas using different methods and instruments. Results converged like rays of light focused on a single point. The comet's brightness remained anomalous, though it began slowly declining as the object passed perihelion and started moving away from the sun. But the most interesting thing wasn't what was declining. It was what was changing. The spectral signature of the blue light showed changes in its structure. The blue beam that seemed relatively stable during the first 24 hours of intense observation began fluctuating. Started showing variations describable as almost periodic. Periodicity was the key word, because periodicity implied control. When natural processes show periodicity, they usually pulsate as a result of external forces: gravitational tides, solar radiation heating, solar-wind interaction. But when a process shows periodicity matching the object's rotation period, as happened with 3I Atlas, it starts pointing toward directed, controlled process, towards something actively responding to the object's rotation, something oriented not randomly, but intentionally. This was a paradoxical situation. The more data accumulated, the less random 3I Atlas seemed, and the more ordered, systematic, managed it appeared. In Avi Loeb's lab at Harvard, a large board hung on the wall listing all known 3I Atlas anomalies, divided into categories: physical, size, shape, morphology, spectral, composition, emission, radiation, statistical, probability. All these characteristics would meet in one object. Kinematic, object behavior, its accelerations, its spatial orientation. With each hour, new data from observatories worldwide was added to the board. And as the board filled, it became increasingly clear that 3I Atlas wasn't a random object. It was the result of some process, the consequence of some cause, the product of some intention. But determining what intention exactly was impossible. Avi Loeb, sitting in his office overlooking Cambridge, received a phone call from the European Southern Observatory director. The director said his team had discovered what they called a second-order anomaly. This wasn't a new 3I Atlas characteristic. It was the behavior of its already known anomalies. The antitail morphology, that strange beam of material pointing toward the sun, had not just a periodic structure, but structure showing signs of what's called phase modulation. This meant not just the beam's intensity changed periodically, but the beam's very shape changed in ways suggesting active control, like someone switching something on and off, or changing something's direction, or modulating something with a complex pattern. Loeb listened without interrupting, then asked one question. Were they certain this wasn't an observational artifact, not a result of interference or data processing errors? The director answered they'd triple-checked the data using 3 independent instruments and results matched. This wasn't an artifact. It was real phenomenon. Loeb thanked the director and hung up. For a moment, he sat in complete silence, gazing out the window where Cambridge continued living its ordinary life. Students walked streets, cars moved along roads, people came and went from cafes. No one knew that in his office something just occurred. A small, greatest realization. Small, but significant. Small, but enough for a person to understand that the world he lived in might be nothing like it seemed days earlier. In the afternoon of November 2nd, Loeb made the decision to upgrade 3I Atlas's rating another step, from slightly above 4 to between 4 and 5. This was carefully formulated upgrading, but an upgrade nonetheless. It meant anomalies had transitioned from serious anomalies requiring deep investigation to serious anomalies beginning to suggest more radical explanations. Loeb knew this upgrade would trigger a new wave of media attention, new debates, new questions, but he also knew the data left him no choice. Honesty toward the data demanded this step. That day, in that moment, as Loeb instructed his staff to prepare a new official statement, letters, notifications, messages began appearing on thousands of computer screens worldwide. Letters from scientists discussing new data among themselves. Letters from observatory directors coordinating new observations. Letters from scientific agency heads asking their teams if they were ready for the possibility that before them stood an object challenging everything they believed about cosmic nature. This was a wave of activity, an electrical current passing through the nervous system of world science. And the heart of this current beat in Harvard's lab, in one person's office, someone who decided simply to say what the data showed. On November 2nd, as day transitioned to evening, a celestial mechanics expert from Princeton University, published an analysis of 3I Atlas's trajectory. The analysis showed that if the object were a simple comet, its trajectory should obey certain celestial mechanics laws known since Newton and Kepler's times. But 3I Atlas's trajectory showed small but detectable deviations from the predicted path. Deviations were minor, just several meters per second in the object's velocity, but they were systematic. They were directed. They suggested the object was experiencing a force unexplained by gravity or solar radiation pressure. This was a force acting selectively, directionally, almost as if 3I Atlas had its own engines or control mechanisms. By the end of November 2nd, 24 hours after Loeb's first rating upgrade, what could be called a paradigm shift in scientific thinking occurred. Not a complete shift, not full acceptance of the idea that 3I Atlas was artificial, but a shift in that this hypothesis, which seemed absurd a week earlier, now seemed like a serious hypothesis deserving consideration alongside others. Started seeming not like a marginal idea of eccentrics, but part of mainstream scientific discourse. This wasn't a moment of discovering truth. It was a moment when the scientific community acknowledged that truth could be different than it thought. And this acknowledgement was the beginning of something new. The beginning of what historians would much later call the moment when humanity stopped sleeping. On November 3rd, 2025, what could be called the officialization of what had until then been an academic conversation took place. At an emergency meeting of the UN Committee on Space Policy, convened in New York in haste, the situation with 3I Atlas was discussed. The meeting was closed, but information about its contents leaked to media within hours. Representatives from 23 countries, including Permanent Security Council members, heard a briefing on the state of observations and scientific conclusions reached to date. The report was delivered by an expert group that included, among others, Avi Loeb himself, serving as scientific advisor. The report contained no sensational claims, no final conclusions. It was what an honest scientific report should be: a description of data, analysis of anomalies, indication of probabilities and uncertainties. But even this cautious report had an effect. Country representatives began asking questions that seemed improper within the UN walls weeks earlier. What if the object really turns out to be technology? Who will lead the response? How will communication be conducted if contact becomes necessary? How will resources be allocated for continued observation? How will information be conveyed to the public? These were questions preparing the organization for a scenario seeming unlikely but not impossible. These were questions about how humanity would respond to the most significant discovery in its history. As a result of the meeting, a resolution was adopted creating a special coordination group called the Coordinated Analysis Initiative for Interstellar Objects, abbreviated CAIO. This group was to coordinate all scientific observations of 3I Atlas, collect and exchange data between all institutions and countries, analyze information in real time, and provide regular reports to the Space Policy Council. This meant 3I Atlas stopped being simply an object of scientific curiosity. It became an international concern, a matter of global significance requiring coordination at the highest level. CAIO was given mandate and resources to become de facto governing body for object research. And heading this group was named Avi Loeb. Recognition that his vision and methodology became the foundation for the official response. In Russia, the UN decision was met with positive pragmatism. Russia agreed to participate in CAIO and provided access to data from all its observatories, including the most secret and advanced instruments usually used for state purposes. This was a significant sacrifice of sovereignty, but one Russia was ready to make for participation in research potentially becoming the most important in human history. The head of the Special Astrophysical Observatory in the Caucasus gave an interview saying, "Science stands above politics, and that at this moment all countries, regardless of disagreements, shared a common interest, understanding what they'd encountered." China, without waiting for official KO invitation, announced its data would be open to all participants, including Western countries. Unusual for Chinese state observatories. This was acknowledgement that facing possible extraterrestrial technology, all concepts of state secrecy and national security stepped into the background. If humanity faced something greater than national interests, then national interests had to align with this greater thing. This demonstrated that even amid deep geopolitical division, humanity had common ground for cooperation, curiosity, fear, and hope before the unknown. In Europe, preparation began for the most ambitious, coordinated observation in European astronomy history. Every major European observatory, from Spain's Sierra de San Pedro in the south to Norwegian stations in the north, was joined into a single network observing 3I Atlas. Data transmitted in real time to a central hub in Geneva, where more than 100 astronomers, physicists, and engineers worked around the clock analyzing information as it arrived. This was science as rarely practiced, science without national borders, science oriented toward a single goal. Each saw the opportunity to contribute to what could be their life's most important work. On November 3rd, as the official apparatus engaged in 3I Atlas research, the research's very nature transformed. It stopped being a project for curious scientists. It became a matter of state, matter of international community, matter requiring organization, coordination, resources at levels usually reserved only for largest scientific initiatives. A special budget was created, additional resources allocated, urgent conferences organized. But most importantly, perception changed. What seemed like Avi Loeb's slightly wild idea a week earlier was now recognized by the international community as a legitimate research area requiring massive resources and official status. As November 3rd transitioned to evening, several significant events occurred simultaneously. In the United States, NASA announced creation of a 3I Atlas task force at its Mission Control Center in Houston. The group was to coordinate all American observations and prepare for any possible scenarios of interaction or contact with the object. In India, Indian Space Research Organization telescopes were reoriented, and the country announced young astronomers would get opportunities working with 3I Atlas data, gaining experience that normally would require entire careers. In Australia, at the Parkes Observatory, one of the world's oldest and most respected radio telescopes was retrofitted to attempt detecting any signals that might come from 3I Atlas. This was an attempt to hear the object, to hear if life existed within it, if intelligence resided there. The night of November 3rd was when the official world recognized what the scientific world began recognizing 2 days earlier, recognized that before humanity stood an object requiring not just scientific analysis, but official, organized, international response, recognized that possibly we lived in a universe more filled, more active, more interesting than we thought. And most importantly, the night of November 3rd was when all humanity, through its UN representatives, through scientists, through leaders, united before the unknown and said, "We will look, we will listen, we will try to understand, and we will do it together." On November 4th, 2025, when world attention to 3I Atlas reached its peak, the first serious alternative hypothesis appeared, offering a natural explanation for all accumulated anomalies. This hypothesis came not from some marginal researcher, but from one of the world's most respected planetologists, Professor Charles Davidson, from the California Institute of Technology. Davidson, whose scientific biography spanned over 45 years and was marked by a dozen highest awards and recognitions, published a preprint proposing comprehensive explanation for all 3I Atlas anomalies based exclusively on natural physics. The hypothesis was clever, well argued, and most importantly, physically possible. According to Davidson's hypothesis, 3I Atlas wasn't just an interstellar comet, but an object that passed through a region of intense cosmic radiation before entering the solar system. This radiation, Davidson suggested, modified the comet's surface layer, removing volatile elements including much iron that evaporated and was lost to space. Meanwhile, nickel found in metallic inclusions inside the comet nucleus remained protected. The blue color was explained by fluorescence of carbon-containing molecules created by cosmic radiation and which, when excited by solar ultraviolet, emitted light in the blue spectral region. The antitail morphology, according to Davidson, resulted from specific nucleus orientation and distribution of active regions on its surface, which when observed from a certain angle seemed ordered, but actually resulted from natural processes. Davidson's hypothesis wasn't completely new. Many of its elements had already been discussed in scientific circles, but combining all these elements into a single logical system explaining all anomalies without needing to resort to artificial origin hypothesis was new and impressive. The hypothesis showed skeptics hadn't surrendered, that the conservative school in astronomy wasn't ready to retreat without a fight before the idea of extraterrestrial technology. And this was good. This was necessary. Science needs skepticism, needs testing, needs its conclusions challenged. Only through such trial by skepticism, fire does truth grow. Avi Loeb responded to Davidson's hypothesis, not emotionally, not defensively, but methodically examining its weak points. In a long letter addressed to Davidson and published in a scientific journal, Loeb pointed out that while Davidson's hypothesis was logical, it required very specific cosmic irradiation conditions, very specific nucleus orientations, very specific distributions of active regions. Loeb performed calculations showing the probability that all these specific conditions converged in one object was roughly as low as the probability the object was artificial. The hypothesis wasn't refuted but wasn't convincing either. It was an alternative, but one requiring its own set of unlikely coincidences. This was a moment when the scientific community began splitting into two camps. Not hostile, not irreconcilable, just seeing the data differently. In one camp were those like Loeb, who saw in 3I Atlas anomalies signs that familiar explanations were insufficient. In the other were those like Davidson, who believed that natural physics, in its fullness and diversity, was sufficient for explaining any phenomena people could observe in the universe. This was a discussion about boundaries between known and unknown, between natural and artificial, between what we think possible and what is actually possible. On the 4th day of November, as this discussion gained momentum in scientific journals and conferences, something important occurred in orbit. 3I Atlas, which had passed perihelion 2 days earlier and was starting to move away from the sun, began ejecting less material. This was natural. As it moved from the sun, the comet cooled and its activity decreased. But the rate at which it cooled and decreased activity was unusual. Standard comet cooling models would predict 3I Atlas's brightness should decrease according to a certain mathematical function, depending on distance from the sun and ice material characteristics. but observed brightness decrease was faster than the model predicted. This suggested the comet was cooling not just from reduced solar heating, but from something else, from something actively removing heat, from something describable as a cooling mechanism. A young Swedish astrophysicist working within the Comet project proposed an explanation for this accelerated cooling. The object, he said, might have an evaporation mechanism more efficient than simple direct evaporation from solar heating, a mechanism using directed gas ejection or heat exchange for accelerated cooling. This explanation raised more questions than it answered, because such a mechanism would require either active control or very specific construction. This was an interpretation sitting on the boundary between natural physics and presumption of artificial origin, sitting on the boundary because the boundaries between them were blurred. As the fourth day of November transitioned to evening, something resembling a scientific crisis began in the international research community. It wasn't panic, it was confusion. Confusion from data pointing in different directions, from different data sets, allowing different interpretations, from truth not simply hidden somewhere in numbers, ready for discovery, but being more complex, more multi-layered, more demanding. Confusion from the scientific community finding itself in a situation requiring greater humility, greater acknowledgement of knowledge boundaries, greater readiness to say, "We don't know." And in science, the words, "we don't know," were often the most honest and most important words a person could speak. On November 4th, as evening over Europe transitioned to night and dawn began over Asia, one more significant event occurred. The International Astronomical Union, the organization coordinating astronomical research worldwide and responsible for official cosmic object nomenclature, convened an urgent board meeting. The meeting discussed the possibility of reviewing 3I Atlas classification. Instead of calling it a comet as had been done since discovery, a proposal emerged to give it new status of Object of Undetermined Origin, abbreviated OUO. This wasn't simply a name change. It was official acknowledgement that the scientific community wasn't completely certain about the object's nature. It was acknowledgement of uncertainty at the highest level of international astronomy coordination. It was acknowledgement that before humanity stood something whose classification required new categories, new ways of thinking, new humility before the face of the cosmos. On November 5th, 2025, as 3I Atlas continued moving away from the Sun, leaving behind a complex history in spectral data and scientific debates, something happened that carried more meaning than any specific discovery or specific result. A shift occurred in how humanity looked at itself and the place it occupied in the universe. This shift didn't happen in a day. It accumulated slowly with each hour of observation, each new anomaly, each upgrade on Loeb's scale. But on November 5th, this shift became visible, tangible, real. It became the moment when people worldwide, regardless of culture, religion, or political belief, began asking the same questions. And these questions were less about the external universe and more about what it meant to be human in such a universe. In schools and universities worldwide, new debates began. Not debates about whether 3I Atlas was artificial or natural. That question could be debated for years without final answer. Debates were about meaning, context, humility. Young students asked teachers questions they hadn't expected. If 3I Atlas was a natural comet with such extreme anomalies, what did this mean for our understanding of physics? If it was artificial, what did it mean for our understanding of the universe, cosmos population, our place in it? If we didn't know the answer, what did it mean for our humility before the unknown? These were questions extending far beyond astronomy into philosophy, spirituality, existential understanding. On November 5th, in Avi Loeb's Harvard office, a meeting occurred symbolic in its composition. Gathered weren't just astronomers and physicists, but philosophers, theologians, social scientists. Loeb spoke to them about data, numbers, what they meant in the scientific method context. But after his presentation, an Oxford theologian asked a question catching Loeb off guard. If humanity faced proof we weren't alone in the universe, how would this change our spirituality, our faith, our morality? Loeb smiled and said he didn't know the answer, but that it was the right question, and the right question was half the answer. Across the planet, people began understanding they lived in a transitional moment. It wasn't a revolution moment with barricades or violence. This was a consciousness revolution, a shift in how people saw their world and possibilities, a revolution beginning not with political manifesto or battle cry, but with simple act of looking upward at the cosmos and seeing something requiring reassessment of all assumptions. On social media, people shared reflections, fears, hopes. Some saw in 3i Atlas a threat, reason for worry. Others saw possibility, a sign that humanity wasn't condemned to solitude in infinite cosmic emptiness. Most simply tried making sense of what it all meant. The night of November 5th, over observatories worldwide, was a night of calm and reflection. Telescopes continued working, data accumulated, but the pace of life slowed. This was a breathing moment when people working sleepless for 5 days could allow themselves to stop and grasp what had occurred. Not a revolution in what we knew about the cosmos. 3i Atlas could be a natural comet, and nothing fundamental would change. A revolution in our readiness to consider what was possible. A revolution in our openness to miracles, to surprises, to a universe more interesting, more active, more filled than we thought. Avi Loeb, sitting in his office the night of November 5th, looked at the board listing all 3i Atlas anomalies. He could erase it, start over, forget it all, and return to normal research. But he knew this was a moment that wouldn't return. This was the moment humanity awakened to new possibility, new understanding that the world wasn't closed, wasn't complete, wasn't fully known. The world was open, full of secrets, an invitation to exploration, questioning, humility. And 3i Atlas, regardless of what it actually was that door opening to the unknown, the door through which humanity began poking its head to see what lay on the other side. When people asked Loeb in these days what he felt, what he thought about what happened, he usually gave the same answer. He said he felt no triumph because nothing was proven definitively. He felt no fear because fear resulted from unknownness, and unknownness was the environment in which science thrived. He felt curiosity, pure, simple, irrepressible curiosity. Curiosity of someone looking at stars, not because he already knew the answers, but because he wanted to discover the questions, wanted to know what questions should be asked to approach truth more closely. And in this curiosity, in this desire to know, in this willingness to be wrong to be right, in this humility before the unknown, here lay the essence of what happened. Here lay the essence of the moment when one comet taught humanity to be honest with itself about the boundaries of its knowledge. On November 5th, 2025, 6 days after 3i Atlas passed its closest point to the sun, 7 days after Avi Loeb upgraded the rating and began saying what was dangerous to say, the story hadn't ended. The story was just beginning, because the true meaning of 3i Atlas wasn't in what it was or could be, but in what it awakened. It awakened humanity to the possibility that the universe was more mysterious than it seemed, It awakened science's readiness to ask questions beyond normal boundaries. It awakened in people an understanding that we don't know as much as we think we do. And in this awakening, in this understanding of knowledge limitations, in this humility before the cosmos lay the path to real progress, real discovery, real beginning of a new epoch in human history. An epoch where people were ready to look upward and see miracle, ready to ask questions and accept uncertainty, ready to be small in a vast cosmos and find in that smallness not fear but beauty, not despair but hope.